This video is going to introduce Hess's law, and then we're going to do a practice problem a little bit later. In order to understand Hess's law, we need to start by talking about state functions. A state function is a function where the value of it does not depend on the path you take to get there. It only depends on the initial and the final states. And we're going to do an example of this to make sure it makes sense. There is a different kind of function called a path function where the value of that function does depend on the path that you took. So an example of this in everyday life would be your house and your friend's house, and he lives across the street from you. Let's say he lives 100 feet away. You could just walk to his house and you would walk 100 feet. Or let's say you took the long route and you went from Frederick down to Los Angeles and you went up to Seattle to get some coffee and you went down to the Keys to go snorkeling. And then you went to Las Vegas to do some gambling, and then you went up to Acadia National Park to do some sightseeing and some hiking. That would be fun. And then you traveled back to his house. So the distance between your house and his house is still only 100 feet, even though you traveled 8,000 miles to go from your house to his house. So the distance between the two houses is a state function. The distance you traveled to get from your house to his house is a path function. Now, the reason why all of this matters is because change in energy and change in enthalpy as well, and some of the other thermodynamic concepts we're going to talk about are also state functions. And so change in energy is a state function. So let's talk about, we have a ball at the top of this hill. Let's calculate the energy that's released when the ball rolls halfway down the hill. The problem with trying to roll the ball halfway down the hill is that it won't stop halfway down the hill. It's going to keep going, right? We can't roll it halfway down because it won't stop. We could roll it all the way down like that, and then we could push it halfway back up like that. If energy is a state function, then this should still give us the same answer, because the initial state and the final state, if we're rolling it halfway down, will be the same as the initial and final state if we do it the way that we know we can do it, by pushing it all the way down, rolling it all the way down, and pushing it halfway back up. So because the initial and final states are the same, then it doesn't matter which path we take to get there. And the reason why this matters is because sometimes in science you can't do the reaction you want, but if you can do other reactions that just take a different path, then you end up with the ability to calculate the parameter you want. And this is an introduction to Hess's law, which is the same idea, but they would be chemical reactions that we would be doing. So delta H is also a state function. Hess's law states that if we take a reaction, and this overall reaction is at the top, 2 moles of NO2, reactive form 1 mole of N2O4. Now, if we can't do this reaction in one step, we could do step 1, where 2 moles of N2 decompose into 1 mole of nitrogen and 2 moles of oxygen. And then we could take step 2, we could take those two elements and recombine them in a new way to make N2O4. So if we can't do the direct reaction, we could divide it into steps. The initial state and the final state are still the same if we do it in one step as opposed to if we do it in 2 steps. So if we look at enthalpy on a vertical scale, we have 2 moles of NO2. Step 1 is going to release some heat to form its elements. And then in step 2, we're going to require some heat and use those elements to reform N2O4. So if we do step 1 and step 2 as a 2-step reaction, that should give us the same delta H if we add them together that the overall reaction would have given us, which is negative 58 kilojoules. So again, the initial state and the final states are the same, and it doesn't matter if we do it in 2 steps or in 1 step. It's just like rolling the ball down the hill. Right? We can do it this way, or we can do it this way. They should give us the same answer. Now, The lab that you did previously, where you were initially sort of understanding the concepts of endothermic and exothermic, this was the sort of the same idea, where we talked about dividing these dissolution into three different sort of parts, where you separate the solute, the solvent, and then bring it together. This is the same idea, where the delta H shown here is just the sum of the individual parts. And so we've already sort of seen this idea of Hess's law in the concepts of the lab that we did earlier. So that would be the exothermic, net exothermic. We also had a net endothermic process. Now, this is another picture showing you Hess's law. This one is from the book, where initially, this is kind of a complicated image. We're trying to do a combustion reaction involving C3H8 reacting with oxygen to form carbon dioxide and water. And so here, one way to do it would be to go straight down. This delta H of reaction is negative 2,220 kilojoules. Another way to think about this is divide it into steps, where the first step is number one, decomposition, where the C3H8 decomposes into carbon and hydrogen. So now all we have are elements. And then we could, in step 2, form 3 moles of carbon dioxide. And then in step 3, form 4 moles of water. And that will give us the same products that we would have gotten if we had just undergone combustion. So we're going to talk about this later. This wraps into an idea of using heats of formation, which we're going to talk about later. So the overall reaction would be the same as individual steps. We're going to do this practice problem for Hess's law, where we're given 3 reactions with corresponding delta H values, and we're going to use those 3 reactions to calculate the enthalpy of a different reaction. So in a Hess's law problem, the way these are usually set up is you're provided with some number of chemical reactions with their corresponding changes in enthalpy, and then you're supposed to take those reactions, take 1 or 2 or all of them, and manipulate them in a way such that when you add them all together, you get the reaction that you're looking for, which is here listed at the bottom. So the reaction at the bottom, we don't know delta H, and we need to figure that out from the delta H's given above. So for simplicity, clarity reasons, I'm going to number these reactions 1, 2, and 3. And I'm going to label their delta H values 1, 2, and 3 just to make that more clear. So I think the most straightforward way to approach a Hess's law problem, since we're trying to reach the goal of getting the reaction at the bottom, I think the easiest thing to do is to start with the first reaction component here, which is 2 moles of carbon, graphite. Find that same component above, and it appears to be in reaction 1. And then look at how it is the same and how it is different in reaction 1 versus the goal reaction at the bottom. And it's on the same side of the equation, which is good. We don't have to reverse the direction of the reaction, but the one at the bottom has 2 moles instead of 1. So we need to take reaction 1. We're going to multiply the entire reaction by 2. So we get 2 moles of carbon, 2 moles of oxygen, and 2 moles of carbon dioxide. And then we're going to take delta H and multiply that by 2 as well. So whatever we do to the reaction, we're also going to do that to delta H. And that gives us a new delta H1 times 2 of negative 787 kilojoules. Next, we're going to find hydrogen. Hydrogen is in reaction equation 2. It's on the correct side of the equation on the left, but it has 1 mole in reaction 2 as opposed to 3 moles in our overall reaction. So we're going to take equation 2, reaction 2, we're going to multiply by 3. And this is what we get. And one thing I want to make sure everybody sees is that this 1/2 oxygen becomes 3/2 oxygen. You got to get over your fear of fractions, okay? If you don't like fractions, you're going to have to get used to them, because we do use usually half or 3/2 or 7/2 or some sort of half fractions for a lot of these reaction components. We're going to take the corresponding delta H2, and multiply that by 3. That's going to give me negative 857.4. The last reaction component is C2H6. That's ethane. Ethane is in equation 3. But there are two differences with the ethane in equation 3 and the ethane in our overall reaction that we're aiming for. One is that it's on the left side of the equation in reaction 3, but it needs to be on the right side of the reaction arrow. So one thing we need to do is we need to reverse it. Another difference is that it has 2 moles in equation 3 and it only has 1 mole in our overall reaction. So we're going to take the entire reaction equation, we're going to reverse it, but we're also going to divide it by 2. Or you can multiply by 1/2, whichever one you prefer to, however you prefer to think about it. So that's going to give me 2 moles of CO2. This 4 CO2 becomes 2 CO2. 6 waters becomes 3 waters. 2 ethanes on the left becomes 1 ethane on the right. And 7 O2s becomes 7/2 O2 because we're dividing it by 2. And then delta H, we're going to do two things. You're going to reverse the sign. So here I have multiplied by -1. That means instead of being negative, it's going to be positive. And we're also going to divide it by 2. So that's going to give me 1559.8 and a positive 1559.8. Now, it's always good at the end. Your goal is to just calculate delta H, which means over here, assuming all 3 of these reactions now combine to give this overall equation, that means all you have to do is add these 3 delta H's together and you're done. You should always verify, however, at the end that they do add up to give you the overall equation. So there's a lot of extra reaction components in here that are going to cancel out. So anything, remember, that's on the left that is also on the right is going to cancel out. You can just cross it out. It doesn't appear in the net overall reaction. So if we locate those things, we're going to add them up. You'll see that 2 carbon graphite shows up over here. 3 H2s is in our overall reaction. And C2H6 is in our overall reaction. So I'm just going to circle those. All these other components should cancel out. So 2 moles of oxygen is the same as 4 halves. So 4 halves plus 3 halves equals 7 halves. So that cancels out with the 7 halves on the right. We also have 2 CO2s on the right and 2 CO2s on the left, so those cancel. We also have 3 waters on the left and 3 waters on the right, and so those cancel out as well. So you do get the overall reaction equation, and then you just add all 3 of these delta H values together to get the overall delta H value. So that's a plus sign, -84.6